We use batteries all day, every day, ranging from the battery of your smartphone to the battery in your car. This technology has been and continues to be crucial to building a more sustainable world. At its most basic, a battery is simply a collection of cells, which convert chemical potential energy into electrical energy. But the electrochemistry behind this process is far more complex than it may first seem. In 1799, an Italian scientist named Alessandro Volta created the first electro battery, which was named the voltaic pile. He stacked alternating plates of zinc and copper, separated by cloth soaked in sulfuric acid. When the zinc was connected to the copper by wire, electricity was produced. This works because of each metal's electrochemical potential, or redox potential. Redox potential is the tendency of a specific element to lose or gain electrons, measured in volts. This is split up into reduction and oxidation potential. Reduction potential is the tendency to gain electrons, and oxidation the tendency to lose electrons. Since zinc has a high oxidation potential, a high tendency to lose electrons, it will oxidize given any opportunity. In the voltaic pile, zinc atoms oxidize to form zinc 2 plus ions, and 2 electrons for each atom. Then the zinc ions migrate into the cloth soaked in sulfuric acid, leaving the electrons behind on the zinc plate. Also joining the electrolyte is copper 2 sulfate, as a result of copper reacting with the sulfuric acid. The surplus of negatively charged electrons in the zinc plate causes it to act as an anode, and so, when the zinc and copper plates are connected conductively, the potential difference results in an electromotive force that moves electrons through the circuit to the copper plate, which acts as the cathode. The electrons in the cathode then reduce the copper ions in the electrolyte due to its higher reduction potential, producing copper. This redox reaction continues, resulting in a constant flow of electricity. Nowadays, batteries have come a long way from the voltaic pile, with lithium-ion batteries at the forefront of rechargeable battery technology. Lithium-ion batteries work off similar base principles to the voltaic pile, with lithium being used due to it having the highest oxidation potential of all the elements, and thereby being capable of producing the most ready supply of electricity. In order to understand how the rechargeable lithium-ion cell works so well, we must take a closer look at its structure. Firstly, we have the anode, which is made from graphite in order to intercalate lithium ions. Graphite is a great material for this as, being porous, it allows the lithium ions to be stored, and a high concentration of lithium ions at that, due to its numerous weakly bound layers. It is also chemically inert, so no unwanted reactions take place. The cathode is made from a metal oxide crystal with lithium added. This is a more stable state for lithium ions and so allows for the discharge process. Typically, lithium cobalt oxide is used as it has the highest energy density. Additionally, lithium has the third lowest density of any element, reducing the weight of the battery. A rechargeable battery has 2 phases, charge and discharge. When charging, the cell is connected to a power source, and so in the cathode, the lithium's outer electrons will be attracted to the positive side of the power source, and are readily lost from the lithium due to its high oxidation potential. The electrons then flow through the circuit to the anode through current collectors, made from aluminium for the cathode and copper for the anode, each to avoid unwanted reactions. Meanwhile, the lithium ions from the cathode de-intercalate and migrate to the anode in order to balance the charge from oxidation by dissolving into the electrolyte. The electrolyte serves as a medium for lithium ion transport between the electrodes. It is usually made of lithium salts dissolved in an organic solvent, such as dimethyl carbonate. The lithium salts allow for quicker charging as lithium ions migrating from the cathode cause other lithium ions in the electrolyte to take their place, speeding up migration. As soon as charging stops and a load is added to the circuit, discharge starts. Lithium ions and their electrons flow back to their more stable state in the cathode, where they are intercalated into the metal oxide crystal. Lithium ions flow through the electrolyte and electrons through the circuit, powering its components. Should the electrolyte dry up due to high temperatures, a non-conductive separator is present that is microporous, allowing lithium ions through but not allowing for a short circuit that would cause the cell to catch fire or explode. Whilst the lithium-ion battery has proven its effectiveness, it leaves much more to be desired. when fossil fuels such as petrol are cheaper, more energy dense, and have higher specific energy values. Fortunately, rechargeable batteries have received an enormous amount of research and development. One of the leading prospects for the future of rechargeable batteries is the all-solid-state cell, having been extensively researched by many leading corporations, from Dyson to Samsung to Maxwell Technologies, which has been recently acquired by Tesla. The only difference between a normal lithium-ion cell and a solid-state one is that it has a solid-state electrolyte instead of a liquid electrolyte. Whilst no solid-state cell has been commercially developed yet, a solid-state electrolyte could allow for much higher cell capacity, much longer cell life, and incredibly faster charging. Additionally, it would make the cell to be much safer, as dendrites would no longer be formed, the cell would have greater thermal stability, and would no longer be flammable. New technologies such as fast, fully electric flight would be possible, and the world would see a decline in the use of polluting fossil fuels as they are overtaken by electric power. But first, we need to find a way of making solid-state batteries commercially available. A solid-state electrolyte has two main functions. It needs to have high ionic conductivity, yet low electric conductivity. One way to achieve this is to employ a solid lattice structure that inherently exhibits defects or vacancies. A vacancy is an empty position in an ionic crystal, where an ion would otherwise be, but is not due to crystalline imperfections. This is known as a Schottky defect. These vacancies allow ions to diffuse through the lattice, whilst the lattice still retains high electrical resistance. What is particularly promising is that these vacancies can be forced by mechanical deformation, rapid temperature change, or even exposure to radiation. Furthermore, ionic conductivity is scaled with the number of vacancies. This would theoretically allow for the large-scale production of efficient solid-state electrolytes. However, creating vacancies causes a charge imbalance in the crystal that would destroy it if not treated. This charge imbalance is treated by aliovalent substitution. Aliovalent substitution involves integrating ions with greater individual charges into the crystal in order to balance the charge. This can be carried out via doping. For instance, we could create vacancies in a lithium iodide crystal and then balance the charge with half the number of doped magnesium ions, leaving a free vacancy for every magnesium ion, thereby allowing lithium ions to diffuse through the crystal. By applying these methods to other crystals containing lithium, many hope to create a commercially available solid-state electrolyte, such as lithium nitride, which, when doped with lithium oxide, sees a definite increase in ionic conductivity whilst retaining a high electrical resistance. These cells have the added benefit of exhibiting Arrhenius behavior, which means that ions travel faster through the electrolyte as temperature increases. This is by no means the only way of achieving a solid-state electrolyte. Research has gone into materials such as polymers or even glass, but we still face many other difficulties in cell production. However, one thing is for sure: should we overcome the challenges we face to developing a cost-effective and mass-produced solid-state battery, the sky would be the limit.